Okay, let's get started, please. So, remember we are talking about non-negative series. So for the last few days and for today as well, we're restricting ourselves to these series where all the terms are non-negative. And you might think, why are we doing that? Later on we'll get, I mentioned this before, later on we'll get to a fact that later we'll see that if the sum of the absolute values converges, then the original series converges. Right, so we'll get this sort of fact, and so it'll be one thing we can do is if you have some series, you look at the sum of the absolute values. Well, that's a non-negative series, right? So it behooves us to have a bunch of ways of checking if non-negative series converges. Okay. So. And what we're in the middle of, remember, is the children of the direct comparison test. Right? The children of the direct comparison test, or what I think we call it the basic comparison test. Okay. So, can anybody tell me? Does anybody remember what the basic comparison test was? Because if we're talking about its children, we better know what it is. Anybody remember it? Can you roughly tell me what it is? It's comparison. Elizabeth, yes, go ahead.
If you have two sequences of partial sums, and one of them is bigger than the other, if the bigger one converges, the smaller one will also converge.
That's true. That's actually a little bit better than the direct comparison test. It's not exactly right, but it's actually what you said is actually a little bit better. So it's if you have two non-negative series, and if the a sub n's are less than the b sub n's past some point, right? Then if the bigger guy converges, then the smaller guy converges. Right. If you have two series and the terms of one are smaller than the terms of the other, if the sum of the bigger guys converges, then the sum of the smaller guys is going to converge too. And the way we proved it is as you say, we look at the partial sum series, right? So that's the fact that we used. So that's sort of like a stronger fact than this. Okay, so that was the basic comparison test, and we were in the middle of talking about the limit comparison test. Okay. So again, just to make sure you know it, can anybody tell? This should be in your notes already, so I don't think you need to recopy it. We're just reviewing what we did last time. Can anybody state the limit comparison test, even if just roughly? Right. So you want to be able to, when you talk, you want to be able to talk about mathematics, right? In high school or in elementary school, maybe mathematics isn't something that seems open to discussion. But actually, mathematics is created by discussion, and you want to be able to talk about it. Okay. So like this basic comparison test, right? You should have this sort of precise thing, but you should also have a rough idea. Try to have a rough idea, like, okay, it's about if you have two series and the terms of one guy are bigger than the other guy, right? then if the bigger guy converges, the smaller guy's going to converge, right? The smaller guy's going to converge, the smaller guy diverges, and the bigger guy diverges, right? Okay, so be able to talk about your knowledge. If you can't talk about it, well, then there's something a little bit wrong, right? Okay, so limit comparison. What's the idea, right? Well, you've got two. It's a comparison. There's going to be two series, right? There's two series. There's A sub n and there's B sub n, and something happens. Something happens, right? There's some sort of limit. There's some sort of comparison, right? Yeah, Maddie.
If you take the limit of A sub n over B sub n,
Right. So
and the
consider.
limit is greater than 0, then they either both converge or both diverge.
That's right. So consider this limit, right? If it exists, and is bigger than, and is bigger than 0, then they either both converge or they both diverge. Right? One converges if and only if the other one converges. There's actually a little bit more of this there, but I'm not going to state it yet. Okay, right, so you look at the limit of this ratio, right, and so if this thing is equals some number bigger than 0, then they have identical, then they both converge or both diverge. Right, so if this limit equals some number, right, some positive number, okay? Put away your phone, please. Thank you. Okay. Can anybody give me a sense of why that ought to be true? Why should that be true? Why should that be true? So think, like the limit of the ratio is L. What does that say to you? The limit of the ratio is some fixed number. So let me show you one way of thinking about the limit. Okay, so here's your intuition. Right, you're thinking, well, look, this limit is L. Right, this limit is L. It's some positive number. And so the way you want to think is that, well, basically, A sub n over B sub n turns out to be basically L. Okay, this is not true. It's not equal to L, but the limit is L. Okay, but you want to think, well, and I had actually my PhD advisor would always say, morally speaking, this is going to be equal to L. Okay, so now suppose it is equal to L. Suppose it is equal to L. Well, what would that tell you? Well, A sub n is going to be L B sub n, right? Okay, what if that were true? Would that tell us that they either both converge or they both diverge? Yeah, absolutely, right? Because one would just be a multiple of the other guy, right? You would have summation B sub n, and you would have summation A sub n, but summation A sub n is just some constant on B sub n, right? And if this guy converges, well, that's going to converge too. If this guy converges, that guy's going to converge, right? This guy, either they both are going to converge or they both are going to diverge, right? Because one is just a multiple of the other. Okay, this is how you want to think, right? What does this mean? Well, this means that basically, morally speaking, that this is going to be equal to L. Okay. Now, it's not true that this is equal to L, but it's close enough. Okay. For the limit to be equal to L, well, it will be close enough to make this phenomenon occur. this is how you want to think mathematically. This is how you think. Okay. Okay. Does that make sense? Seth, do you have a question? No. Just wiping your nose. Yeah. Okay. So. Okay. So everybody get the idea of the limit comparison test, right? If the limit equals L, well, basically that tells you that one sequence is a multiple of the other sequence. So they're both going to converge or they're both going to diverge. That's the idea, right? Okay, let me show you the actual proof. Okay, here's the actual proof. You say, well, look, consider A sub n over B sub n. Okay. And say that this is L. Okay. So eventually, it's going to be, pretty close to L, right? So since the limit of A sub n over B sub n equals L, as n goes to infinity, eventually A sub n minus B sub n, A sub n over B sub n is going to be between here and here. Okay, it's going to be between L over 2 and 3L over 2. Eventually, this is going to happen, right? A sub n over B sub n is going to be capped between L over 2 and 3L over 2. Right? And by eventually, I mean the existent n past which, right? The existent n past, right, such that if n is bigger than n, right? You put that in mathematical notation. Right? There's a time past which this is going to be true, right? Because the limit is L. Right? Everybody okay? Okay, so in that case, what do you see? Let's multiply everything through by B sub n. Past that point, we have L over 2, B sub n is less than A sub n is less than 3 over L over 2 B sub n. Right? I just multiplied through by B sub n. B sub n is positive, remember. Okay. Now what am I going to say? How does this show me that if the sum of the A sub n's converge, then the sum of the B sub n's converge, and if the sum of the B sub n's converge, then the sum of the A sub n's converge? I'll give 2 points on the final for the person who tells me the right thing right now. Elizabeth.
Can you use the squeeze theorem?
It's not the squeeze theorem. Sure.
By direct comparison.
By direct comparison, exactly. Yeah. Right. This, in fact, that's sort of like that's going to happen, right? Because this is the child of the direct comparison test. Right. So what happens? Well, you say, well, look, this guy is a bigger sequence than that guy, right? So by direct comparison, by basic comparison, if summation A sub n converges, summation L over 2 B sub n does, right? But if summation L over 2 B sub n does, so does summation B sub n, right? Because it's just some constant times that guy, right? And similarly, right, if summation B sub n converges, then summation 3L over 2 B sub n does also, and by by basic comparison, summation A sub n does. Right. So if the A sub n's, the sum of the A sub n's converges, the sum of the B sub n does. If the sum of the B sub n converges, then the sum of the A sub n does. Okay, so I hope everybody sees how limit comparison follows from basic comparison, right? You use basic comparison to get limit comparison. Any questions? Right. So there's this idea, right, that well, basically, A sub n over B sub n is a constant, right? Morally speaking, this equals that. It wasn't true, right? It's not equal, but it's close enough, right? A sub n over B sub n is not equal to L, but it's trapped between L over 2 and 3L over 2, right? It's not equal to L, but we can trap it between L over 2 and 3L over 2. Right, or we could trap it, it doesn't have to be L over 2, we could trap it between here and here, 3L over, it's not that important. Some constant times L, and some other constant times L. Right, that was enough. Any questions? Okay, so let's go on to the second child of the basic comparison test, which I'm going to make the so-called root test. There are two other children. One is called the ratio test, and the other the root test. Let's make the root test the next one. Okay, root test. So here it is. You have summation A sub n, a non-negative series. Okay, and the limit of the nth root of A sub n is some number, rho. Okay, this is the Greek letter rho. I know it looks like a P, but it's not a P. How many of you have seen the root test before? Nobody? Okay. Can anyone guess what I'm going to say? What's going to be the conclusion? If the limit of this thing equals to some number rho, it's kind of a hard one. Let me just write it out. If this equals some number, if rho is less than 1, right, it's going to be some positive number, or it's going to be some non-negative number, because these guys are all non-negative, of course. But if that number turns out to be less than 1, then the series converges. If the number is greater than 1, then the series diverges. And if it equals 1, then you don't know anything. So we don't need to put anything up. If you want, you can say if it equals 1, then you don't know anything. But so no relation. So right, so let me give you an example. Yeah, okay. So for example, if I look at so here's a pretty straightforward example. The sum of powers of natural log, sum of 1 over powers of natural log, as those things, as powers go from, as k goes from 2 to infinity. Okay, so this is pretty simple. What does the root test say to do? It says take the limit, consider the limit of the kth term, the kth root of the kth term. Right? Consider the kth root of the kth term. Okay. Well, what do you get? This 1 over k and the k are going to cancel out with each other, right? And you get the limit as k goes to infinity of 1 over natural log of k. Right? Well, what's that? That's going to be 0, right? That's 0. Okay, so that's our row, right? That's our row, right? You go back and the test says, okay, it's going to converge then. Says that the series converges. Okay. Another example. Summation k times 2/3 to the k as k goes from 1 to infinity. Okay, take 1 minute or half a minute and tell me what happens. Okay. Talk to somebody nearby and say it converges or it diverges. I didn't talk with Kristen. Oh, you already talked. I guess it's too quick. Okay. Who would like to tell me what you got? What happens? Anybody? Sam?
Does the series converge because the limit is 2/3?
Yeah, the limit will be 2/3, right? So you say, okay, let's look at the nth, the kth root of this thing. So you get this thing, 1 over k, right? Well, that's going to be k to the 1 over k times 2/3. As k goes to infinity, right? But the limit of k to the 1 over k as k goes to infinity is 1, right? So you end up with 2/3. So I hope you know that if you don't use L'Hopital's, you need to use L'Hopital's rule and the logarithm. So in any case, so we get convergence. Right. Let's see. what if you try to apply it to something like this? What's called the harmonic, we haven't given it its name, but this is called the Harmonic Series. Okay, we actually know about the Harmonic Series. What does the Harmonic Series do? Converge or diverge? It diverges, right? This thing we actually know it diverges by the integral test. Right? But if we apply the root test to it, well, we're going to get 1 over n to the 1 over n as n goes to infinity. Right? And that gives us a 1. Right? Is that okay, Anna? Yeah. Okay. In comparison, if we look at the sum of 1 over n squared, what do we know about this thing? Does it converge or diverge? It converges, right? This thing converges, again, by the integral test. Right? And if we look at this, well, what do we get? We get, this is also going to be 1. Right? Okay, we got 1 again. So what this says is that if you get a 1, you don't know what's going to happen. If you get a 1, it could be convergent, it could also be divergent. Getting a 1 doesn't tell you anything. Okay, this is just giving you some examples of seeing why that getting a 1 gives you no information about it. Okay, so getting a 1 tells you nothing. Okay, one last example, one last exercise for you. Summation k to the k over 3 to the k squared. Okay, turn to somebody nearby and tell them. Okay, what's the answer? You'll look at the kth root of this thing, so you get k to the k to 1 over k. You get 3 to the 2k to 1 over k. Right? So what's going to happen? You end up with the limit of k over 3 squared as k goes to infinity. Well, that's going to be infinite. That will also tell you that it diverges. So if the row is infinite, that's also going to be divergent. Okay. 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 So now let's see if we can get the idea, like the intuitive idea behind the root test. What's the idea? Right. again, we want to think in this like, rough way of saying what the limit being equal to rho is basically, we're saying that the nth root of a sub n equals rho. That's not true, but morally speaking, that's how you want to think. That this thing equals rho. Okay. First person who can tell me what is going to happen next? No. Who can explain this? If rho is less than 1, you get convergence. Rho bigger than 1, you get divergence. Why would that be true? You need to say 2 words. If you say those 2 words, then you get the promise. I know, 2 points. What is the idea? What is the series? Seth?
Is it strictly increasing?
No. Those are not the 2 words. Those are 2 words, but not the 2 words. Seth?
Integral test?
No. Mira?
Is that something to do with the p-test?
No.
Limit comparison?
Nope. The answer is Kara?
Because it's monotonic.
Monotonic? No. The answer is geometric series. Geometric series. So look. Right. Look at this. This is a sub n to the 1 over n equals rho. Right? If that were true, what would that tell you? That a sub n is rho to the n. Right? Rho to the n. In other words, your series is basically summation rho to the n. Right? Okay. Now remember what you knew about geometric series. Right? If the ratio, if you're taking a geometric series, remember we looked at this thing here, summation r to the n, it's going to be 1 over 1 minus r if r is less than 1 in magnitude. Right? Right? So that's the idea, right? And if it's bigger than 1, it's definitely going to diverge. Right? Because you're summing powers of something that's bigger than 1. Okay, so that's the idea, right? That if this is true, then basically your series would be a geometric series, right? And so if it's less than 1, you're going to get convergence. If you get greater than 1, it's going to be divergent. Right? That would imply this, that would imply this. Okay, so that's the idea. That's the idea of the root test. Okay. Now again, let me show you how one proves it. Okay. So okay. So you look at root. You look at this sequence. The nth root of a sub n. Okay, and here is here is your rho. Okay, so rho is this number, and let's say that rho is less than 1. Okay. Okay. So, right, eventually, so consider this thing. Eventually, and again that means there's past some n, we have that this guy is going to be less than, let's choose some number here in between rho and 1 and call it mu. Okay, so choose a mu between rho and 1. Choose a mu between rho and 1. Eventually, we're going to be less than mu. Right? Because we can trap, we know the limit is rho, right? So eventually we can trap it between here and here, right? Well, that's certainly less than mu. We can definitely make them less than mu. Okay. But then, past that n, a sub n is less than mu to the n. Right? By our knowledge of geometric series, we know that summation of the mu sub n's converges. Right? And these guys are the bigger guys. So by basic comparison, right? So by basic comparison, the smaller guy converges. Any questions? Any questions? Makes sense? Right, so if the ratio is less than 1, you've got convergence. If the rho turns out to be less than 1, you've got convergence. And I hope you see how we would show if it's greater than when you have divergence. Take a minute and see if you can sketch it out. Just like, how would you toggle this argument? If it's bigger than 1, then how would you switch this argument around a little bit to show that you diverge? See if you can do it. If you can't, that's okay. If you can, that's great. Do you have the answer now? No. Can we what?
School geometric series.
Okay. In a minute. Yeah. I mean, actually, let me do it right now while people are working. So remember, if you have something like this, right, then if the magnitude of r is less than 1, then this thing converges. Right? And the magnitude is bigger than or equal to 1, then you have to get divergence. Okay. Does anybody, was anybody able to see how it would work? If your rho was bigger than 1, then how would you say? Well, you'd say, well, did anybody figure out what to do? Anna?
N sub A, root N of AN is greater than the mu.
And where is your mu?
Somewhere between rho and 1.
Exactly. So you take this other guy, take a new mu here between rho and 1, right? Eventually, this thing is going to be bigger than mu, right? Eventually, this is going to be bigger than mu. So what does that tell you? That past that point, A sub n is bigger than mu to the n, right? By the geometric series, the smaller guy diverges, right? And so, by basic comparison, the bigger guy diverges. Kara?
Did you change what rho was?
Yeah. So we're showing the second part of the statement here, right? So if rho were smaller than 1, we saw that it's convergence. And I was asking, what happens if rho is bigger than 1? Can you see how that shows the series diverges? Right. So Hannah, I'll give you 2 points on the final for that. Oh. Okay. Did anybody else get points during this class other than Hannah? Okay, great. Sorry. Thank you. I should write this down. Okay. So I hope you are seeing how this stuff works. So that's the second test. Let me at least state the third test. So the third test is called the ratio test. And it says, and sometimes people call it the limit ratio test. But anyway, just the ratio test. So you have some series, and this one is a positive series. Okay, and you consider the limit of the ratio of successive terms. Okay, you consider the limit of the ratios of successive terms. Okay. So if that limit exists and if that ratio is less than 1, then you get convergence. Right? Then the series converges. If the ratio is bigger than 1, you get divergence. Okay, we don't have time to talk too much about it, or even show you how to use it, but I wonder if anybody can see what the key idea is this time. Again, there are 2 words you need to say. Proceed.
I think we're going to use the same idea as the other one used about the molarity thing.
Yes.
You compare and then you say AN plus 1 over AN equals to rho.
Yes.
So it means AN at AN, the multiples of each other.
Yes.
So if then rho is greater than 1, that means AN is
You're so close.
means
What kind of a series are we going to be talking about? What series is this, morally speaking?
the one which is not geometric.
Eh?
The one which is not geometric.
The one which is not geometric. What do you mean it's not geometric? Okay, see you next time. Okay, that's it for today. It's like those old stories. If you want to know what happens, you have to read the next chapter.